Let's review some properties of logarithms, and then use some of those properties to make taking a derivative easier. So here, I have some pretty basic properties of a logarithm, that the logarithm base a of a is 1, and the logarithm base a of 1 is 0. Thinking about a logarithm as an exponent, this statement here says that a raised to the first power is a. Certainly true. This statement says a raised to the 0 power is 1. These are the inverse function properties of the logarithm, but if I think about them in terms of logarithms, this one says a raised to the x power is a to the x, and this one simply says the log base a of x is equal to the log base the log base a of x. Here I have the three laws of the logarithm, reminding me that if I take the logarithm of a product, I can rewrite that as the sum of logarithms. The logarithm of a quotient can be rewritten as the difference of logarithms, and the logarithm of m raised to a power can be rewritten as p times the log base a of m. And then finally, the change of base formula, which would let me reimagine a given logarithm with any new base I wanted. Most of the time for us, we like base e. So if I had a log base a of m, I could rewrite that as the natural log of m over the natural log of a. And there's nothing special about the logarithm. In this instance, I could do this with any base I wanted. All right, so a nice review of logarithms. What I'd like to do now is take a derivative two different ways. One way, the first way, just using rules of the derivative I already know. And then the next way will be utilizing the laws of the logarithm to rewrite the function. But first, let's just look at this function and find the derivative. So, if I was just to approach this by using rules I know, the derivative of the natural log of u is 1 over u times the derivative of u. So I need to write 1 over that, and I'm going to skip a step and just write its reciprocal, 1 over what's on the inside u, times the derivative of u, and what I need to do now is the quotient rule. All right, so the bottom gets squared, and then I have the bottom times the derivative of the top minus the top times the derivative of the bottom. All right, let's see if I can do some simplifying, at least on the top of that fraction. Let's see, I'm going to have a 2x cubed plus 2x minus 2x cubed plus 2x. All over x squared plus 1 all squared. All right, well I have an x squared plus 1 and an x squared plus 1 all squared there, so I can cancel one of those. On the bottom I'll have x squared minus 1 times x squared plus 1. And here on the top I'm just left with what this simplifies to, and the 2x cubes cancel, and I end up with a 4x. And there's my nice happy derivative. If I wanted to, I could multiply the bottom out to be an x to the 4th minus 1. And since I've said that, I might as well just go on and write it. All right, so we've taken that derivative. I had to take a reciprocal and use the quotient rule. Let's see if I can use the laws of the logarithm to change my work just a little bit. So what I'm going to do this time is I'm going to say, well, this function is the logarithm of a quotient, so I can certainly use the quotient rule for the logarithm. But on the top, I'm going to go on and factor that first, because now I see the top as a product. And this is where in my algebra class I expanded logarithms as the sum and difference of logarithms. Those instructions would often say express all exponents as factors, but in this one all I have to do is use those laws of the logarithm to rewrite my function, and now I'm just going to take the derivative of this. So y prime is equal to 1 over u, the derivative of x minus 1 is 1, plus 1 over u, and the derivative of the inside x plus 1 is 1, minus 1 over x squared plus 1 times the derivative of the inside is 2x. And I end up with this statement. And I'm looking at it, I'm thinking, well, that doesn't look exactly like my last answer. The hard work I had to do involved the logarithm, but now I'm wondering what I would need to do to be able to rewrite this like this. And as you can imagine, all I have to do to convert one to the other is find a common denominator and add and subtract those fractions. I'm going to let that bit of algebra be an exercise for you, but they are equal, and I find this way a little easier, that I just use the properties of logarithms and it gives me an easier derivative to take, and this answer is just as valid as that one.